and then
Okay, so let's get started, guys. Since I did the old exam on Monday, unless you guys have dire problems, like one or two of them, I can redo them, but all of them are online on Blackboard, so you can just go there to see them being done. Today I'll do some different problems. Is that good? So these you guys don't really have access to, but on number 14 though, on the homework, that is a really good example of a big O and little o problem. And in one of the classes, Dr. Crush went over them, or did they do it in all of the classes? Okay, so I'll go through number 14 from the homework, and then that should be enough for big O and little o. So you have to show whether these are true or false. The first one was x is equal to little o with parentheses x. This is our f of x. This is our g of x. So we can write the limit as x approaches infinity of x over x. That can be simplified to equal 1. Since the original statement was saying that these are f of x is with little o to g of x, and we got 1 as an answer, this means that this term is not little o, so this is false. What would the 1 represent? Big O. So this is big O. Part B, it was x equal to little o in the quantity of x plus 5, I believe. So then we do the same limit again. Limit as x approaches infinity of x over x plus 5. What does that equal? That equals 1 again. Which again, this is not little o, so this statement is false. Any questions on these two? Well, you would solve it, and you'd have infinity over infinity, so you'd do L'Hopital's. Or you can just do it by sight. Both of them are going to go to the same because they're both the same exponent power or degree. C is x is equal to big O. This time it's x plus, we'll go with x plus 5. I can't really read what she wrote, but it's the same thing as the first one, essentially. We know that this is equal to, or we can just say x over x plus 5 is less than or equal to 1 for x is greater than or equal to 1. This 1 would be our m value. So this is a true statement. Yeah.
So how did you get your 1 for m?
When we do x approaches infinity just by looking at it, we know that essentially it's doing what's up here. Like when we reach high values of x, this 5 isn't going to do anything. So this number will always be less than or equal to 1. At infinity, it'll reach 1, but any number slightly less than infinity, it'll still be almost equal to 1. So we can just go ahead and make that assumption. That 1 would be our m value, and we'll just say, so it is big O in that sense. this might make it a bit clearer. We have d x is equal to big O of 2x. So when we put f of x over d of x, we have x divided by 2x. That's equal to 1/2, which is less than or equal to 1. This would be our m value, and so this is true. Your m value should just be the highest integer most of the time. That's how I think about it. Like it's 1/2, but the next integer is 1. But even if you think about it with the infinity, the 2 is not gonna, it's infinity over infinity, so just go with them. No, because you will have example for, say it's x over 2x plus x over x plus 5 or something. This would be 2, because then each of those would be like 1s. This would equal like 3/2. So you 3/2, so you can say less than or equal to 2. So this would be a 1/2. This would be 1, so it's 3/2. But our m value would be 2. Yeah.
There was one note on our notes that it was less than 1/2.
Less than 1/2.
Yeah, and that's what it's in our like
Oh.
and they set it for like x greater than.
Okay, I'll look at that after we do these few homework problems. You won't really ever be tested on this. Let me just say that. I don't think I even had a single exam question on big O and little o, but you never know. So just go along with it. E. We have e to the x equal to little o of e to the 2x. You can do the limit as x approaches infinity of e to the x over e to the 2x. That's equal to 1 over e to the x. That is equal to say, oh, but then she says, yeah. So that's equal to 0. So this is true. Plus the problem mentions it being a little o. For f, we have any questions on that? We have x plus the natural log of x equal to big O of x. So we're testing for big O. We can just do x plus the natural log of x all over x. That's equal to, if we were to separate it into 2 parts, 1 plus the natural log of x divided by x. Now in this will always be 1. But this part, it will always be less than 2, but close to a 1 value. So this is our m. And then for x is greater than or equal to 1, because natural log can't be less than 1. X can't be less than 1 for a natural log number.
How did you know that was less than 2?
Because natural log always approaches a certain value. I'm not exactly sure, but I don't think natural log will ever, the x will always be bigger than natural log. That's right. because you have to think of this as like overall, if they could be equal, it'd be 1. So then you go to the integer 2, but this will never reach 1. So then we do less than.
Oh, the whole thing is.
Yeah.
Okay.
The whole, and this quantity could be like a fraction. The greatest it can be is 1, and then less than 2. I'm not exactly sure why there is not an equal sign, but I think it's because this will never ever be close to entirely a 1 value.
So how would your x be equal then? Like x is equal to that?
X, because then natural log of 1 is 0, so then this quantity can still be 0.
Okay, so
Yeah, this entire quantity can still be 0, so it just, x can never be less than 1, because that's not possible with the natural log. Did that even slightly make sense?
True.
What?
Is that true?
So this one, yeah, would be true.
Is it possible to have a false figure?
False big O? Yeah.
If you pick like the next biggest thing, then why is it ever false?
It means, big O means that it's growing equal to or less than. Then you just have to do like diverging and LCT. That's why I'm saying you'll never actually use this. But in case they ask and you're going to test for a big O, what I would recommend is that you break up the fraction into 2 parts. Essentially, how many parts you have, that's the m value. And then you put a less than sign.
Have one and then L and X over one.
Yeah.
You said you didn't have any questions about this on your test?
I'm just showing you guys this. Well, this is recording. So we're just doing a homework problem. Moving on to the next one. And I'll do like a general process for it once we get through these. G. Natural log of x equal to little o times the natural log of 2x So essentially, whenever it's a little o, you do the limit. Limit as x approaches infinity. So we have the natural log of 2x divided by, the natural log of x divided by natural log of 2x. This one, we can't really just directly see it. We know we need to do L'Hopital's on it. Limit as x approaches infinity. Now we have 1 divided by x all over 2 divided by 1 divided by 2x.
It's 1 over 2x times 2.
Oh.
1 over 2x times 2.
You times it by 2, yeah. So that's equal to a 1. So this is false. It's not little. So here's what you need to do. If you're testing for little o, you do the limit as x approaches infinity. If you get a 0, you're good. Otherwise, it's not little o. Okay? Then the next step should be to test for big O, which would involve you putting them like this. Now, every problem I have seen, you should get an m value. So if they were to give you a problem, just from my past experience, if it's not little o, it will be big O like that. Okay? And then the very last one. Square root of x squared plus 5 equals big O of x. So then if we're doing big O, we just do f of x over g of x squared plus 5 divided by x. Bringing x squared into the parentheses, we have x squared plus 5 divided by x squared. That is equal to the square root of 1 plus, that would be 1 plus 5 divided by x squared divided by 1. Now, they say this is less than or equal to a 3. Yep. I think what they were going at is you have 1, the square root of 5 is greater than like 2 or something. What?
I think it's less than 3, less than 3.
I say it's less than greater than like 27.
I will say this though. You can say this is true because it's not equal to 0.
So you really don't have to do all that?
You do?
They do want like an M. Like,
Yeah.
how will they phrase the question?
I've never had this on exam. So no, they taught this to us, but they never tested us on. So then I never studied enough, and I don't know how they'll phrase the question. So the steps that I will say that will get you the most points will just be if we have a little o of x, the first step will be to do the limit as x approaches infinity of f of x over g of x. So this is, like, I've never had a question, so I don't know how they'll phrase it. But if they ask you whether this is true or false, you do the limit as x approaches infinity, and if you get a 0, then it's true. This is f of x only. Yeah. Yeah. That's what you do if it's with a little o. If it's with a big O, you do f of x over g of x. You try to separate it into 2 fractions. So you have some number that plus something like that. Yeah. So for this we had, or if you can't, it doesn't matter. For this we had just x over 2x. And we know this is just like one quantity. So we can go ahead and say less than or equal to 1 and say this is our m. And then we know it's true since it's not equal to 0. That's, yeah.
Why don't they just let you do this? Okay, so suppose that is true. So you just do the limit no matter what. And if it's 0, then both little o and big O. And if it's a number, then it's just big O.
If you are given, if you don't know whether it's little o or big O, okay? You don't know that, you're given f of x and g of x, the first thing you should do is test for little o. Okay? You do that, and then you see if you can separate it into 2 quantities and then get an m value. Does that make sense? And I'll quickly see.
You have to do it. So for little o to be true, it has to be.
Yeah.
For big o to be false, it has to be.
Yeah, and then you do have to show the m thing for full points. But, okay. But essentially, I would focus on the limit comparison test and divergent, whether the direct comparison test over any of this stuff. And you said in class there was an M value, which in that one, okay, I'll just quickly do that. F of x is equal to an x. So I'll just do limit as x approaches infinity of x divided by 2x plus 1. We do L'Hopital's and stuff. No? You do? You did 1 divided by x. She divided everything by an x. This equals 1/2. So we know it's not little o. So it's not equal to 0, so not little o. And then you do s over 2x plus 1. You break it into 2 parts, yet or not? And then she just did 1 over 2 plus 1 over x, which is less than 1/2. For x is greater than 0. And she named this the m value, or very top. First of all, you can't break this into 2. Don't think about breaking into 2 because it's being added in the denominator, okay? So don't make that mistake. Otherwise, or just by trying to simplify it, what they did was they multiplied 1 over x all over 1 over x to get it into this form to see what would happen as x approaches infinity or whatever. And you know it's got to be less than 1/2. Because this is us solving the limit. This is like, this will go to 0. This is when x like reaches infinity as a limit. This is just looking at x greater than 0. Yeah. Okay. Having said that, any other quick questions on this? Yeah.
Would you, if you did both solve zero, is it wrong? Since
No. Because you'd still get 1/2.
they said that it was wrong.
Did they? Well, in this one, if you put in infinity, you do have infinity over infinity. So then it wouldn't be wrong. The one that they did in class had like a 0 over a number or something. So then that one you don't do L'Hopital. But having said that and confusing you all, we're gonna move on. Because this is really not important.
there gonna be a lot of willow that goes on?
There will probably be none. Yeah. The main test that you need to understand is the limit comparison test and the direct comparison. Okay. You guys also asked me when it does not equal or does not exist. You remember that? Because the options equal. One second. So like we did the problem where it equaled plus or minus infinity. Because this equals 1 and then 0 can lead to plus or minus infinity. But so this would be an example of plus or minus infinity. An example of does not exist is when it repeats continuously and you try to solve it by trig manipulation and it still doesn't come out right. That's what Parsons said. When I don't, okay, this is the closest to an example I can come up with, but it solves that. We have a limit as x approaches pi over 2, and we have cotangent of 2x divided by cosecant of 2x. Okay. So if we have pi over 2 here, we have cotangent of pi which is 0 because sine of pi is 0. Let me write that down. So this is a cosine of 2x divided by sine of 2x all over cosecant is 1 over sine. If we were to plug in pi over 2 into these values, they would approach 0, leading this to be infinity over infinity, and not 0 is 0. Be patient. If you were to just directly see that it would be infinity over infinity, you continue to do L'Hopital. What's the derivative of cotangent? Negative cosecant. Derivative of cosecant, negative. So 2 times cotangent of 2x cosecant of 2x. These would cross out. One of the cosecants would cross out. So you're left with. So you should put the limit as x approaches pi over 2. We are left with cosecant of 2x divided by cotangent of 2x. If you do that again, L'Hopital, you are left with the same thing again. We'll be left with cotangent of 2x now divided by cosecant of 2x. Okay? And if you keep on doing this, you'll get the same thing again. Okay? When that happens, it does not exist. But in this case, we can simplify. Okay? So if you have a problem where this keeps on happening over and over again, the problems you will be given, you will always be able to rearrange. Does not exist won't matter, but that is how you may get it does not exist as an answer. Okay? Did that make sense to everyone? If you keep doing L'Hopitals and you get the same thing over and over again, one thing you can try is to simplify it. And if you can't simplify it, then the answer will be does not exist. But in you guys' case, you will be able to simplify it. So for this one, we can see that the signs go away. We are left with limit as x approaches pi over 2 of cosine of 2x, which is cosine of pi, which is equal to negative 1. So in this case, you are able to simplify it, so you get a negative 1 as your answer. If you couldn't simplify it, and I can't think of an example, or I haven't seen any, then it does not exist if it repeats over and over. Any questions on that? Well, let's do some rate stuff. So you have to prove whether it grows fast or not. Limit as x approaches infinity. So this is just like a normal problem now. Okay, this shouldn't be that difficult. So you guys can try solving it. I'll give you guys like a few seconds. See. So this is like a normal problem, what you may have on the exam.
Grows faster. Slower.
The same?
The same.
Yeah, yeah.
So then that's between 0 and 1, or 0 and infinity. Same rate. And you do need to state all of that. This actually may very well be like a problem you will have on the exam. You guys see like what happened here? We divided by 1 over x. This 1 over x, when it's put under the square root sign, it's squared. So then this x squared goes to a 1. Those drop out and such. So this could have been like a 2x squared, so it'd be a 2. So you would have 1 over square root of 2 here, which would still mean that they grew at the same rate. Any questions on this problem? So you will definitely have something like that. See if whether f of x grows at the same slower or faster rate as g of x as x approaches infinity. Yeah. Yeah. let me see if I have an example of a limit comparison. You guys all understand whether it's improper, so you need to show the limit as b approaches infinity and stuff? Sure. That's also very important. We have to say that, what's the first thing that we should always state? In proper sense, upper limit is infinity. Then we can rewrite this as limit as b approaches infinity from 1 to b of 3x plus 1 minus 2 power dx, or u is equal to 3x plus 1, or du is equal to a 3 dx. So we multiply the inside by a 3, outside by 1/3. We have limit as b approaches infinity of 1/3 times 3x plus 1 to the minus 1 divided by negative 1. From 1 to b, and you can solve it. Oh wait, no, I should show you that. Because they still want you to write it as with a b. So negative 1/3 limit as b approaches infinity. Inside we would have 1 divided by 3 times b plus 1 minus, we put in a 1 here, we would have a 4. This negative 1, we pulled it out, make it a negative 1/3. Made it a negative. So then we would have 1 over 4 here. Yeah. And then you then show that this goes to 0 and solve it. But I don't know the answer. I made it up. Any questions on that? But did you get, so showing that is very important. Showing the limit as b approaches on the out into infinity is important. And then showing that all the way up to the step with b inside it when you plug in your upper limits is important for points. Yeah.
So it's only when both of the boundaries are improper is when you want it from the left and from the right. So if you have negative infinity,
It's when you have infinity in between. Did the practice test have an example like that? No. What? Yeah, we need to split the integral. Yeah. Like x minus 1 was in the denominator, or x plus 1, and the symbol went from a negative 2 to 0 or something. When it's equal to a negative 1, this would be wrong. So then you need to split it into two integrals, one approaching from the negative side, one from the positive side. Are you guys good with this problem? So the main step. What? Yeah, then you evaluate that. Yeah, it is.
So for splitting it into two variables, like you talked about,
Yeah.
like one would have, like its upper limit would be A, the other one would be its, or its upper limit would be its lower limit, and then it's after the second one.
Yeah. There is an example on the video with that. And I did an example on Friday. I think it was like that. Okay, just a quick, this problem is pretty important too. Limit as x approaches 0 of 1 minus, we'll go with the cosine of x, 3 over x. If we plug in a 0 directly, this doesn't work. Cosine of 0. If we plug in a 0 in here, we get 1 to infinity. Okay? So then what we learn is that we need to use the natural log in those cases. So we have y equal to 1 minus sine of x to 3 over x, that quantity. The natural log of y is equal to 3 over x times the natural log of 1 minus sine of x. You guys remember those? So now we do the limit of both sides. Limit as x approaches 0 of the natural log of y is equal to the limit as x approaches 0 of 2 natural log of 1 minus sine of x divided by x, and that should be a 3. This, when we plug in a 0, we get 0 over 0. So we do L'Hopital's. Limit as x approaches 0, we have 2 over 1 minus sine of x times minus cosine of x, everything over a 1. If we plug in a 0 now, we have 2 times a negative 1 divided by a 1 minus 0. That's equal to, why am I doing it? That's a 3. So the answer is a negative 3. But we're not done yet. Therefore, now we need to do e to the power of natural log of the limit as x approaches 0 of y, and that's e to the power of negative 3. So our answer, therefore, is limit as x approaches 0 of y, which we know what y is, equal to e to the negative 3 power. So that would be our answer. So in those steps, you do the natural log of y, do the same limit of both sides, and once you get where the natural log, the limit of the natural log of y equals to a number, then you take, then you do e to both sides. Any questions on that? Any questions? No? Okay.
She's done that.
Okay. If we have the integral x plus 2 divided by the square root of 1 minus x squared, what should we do here? We can break that up. X dx divided by square root of 1 minus x squared plus the integral of 2 over square root of 1 minus x squared dx. And then you guys know how to solve that. What do you do here? U equals that. What do you do here?
Inverse sine.
So this is 2 sine inverse of x. Good.
No! What does that sound mean, Daniel?
There was nothing there. It was okay. Good. I mean, that wasn't really a problem. That was just to show you guys. Say we have now x to the fourth plus x minus 1 divided by x plus 2. Fine. That one, what do? We divide. What do I write in here? X to the fourth plus 0x cubed plus 0x squared plus x minus 1. Did you guys remember that?
Yeah.
Don't make the mistake of not putting the zeros there. What's the first thing that goes up here? X cubed. So it's x to the fourth plus 2x cubed. We subtract that quantity. We are left with a minus 2x cubed plus 0x squared plus x minus 1. What do I multiply here? Yep, so we have a minus 2x cubed here. Negative 2x squared times a positive 2 is a minus 4x squared. We subtract that entire quantity. We are left with a positive 4x squared plus x minus 1. And so, okay. So what do we multiply by now? So then we have a 4x. 4x squared plus 8x. We subtract that quantity. We are left with x minus 8x. So we have minus 7x minus 1. What do I multiply by now? Negative 7. Minus 7x. Negative 7 times 2 is a minus 14. divided by, we subtract those quantities, we are left with a negative 1 plus 14, so it's a 13. So this integral can be broken apart into x cubed minus 2x squared plus 4x minus 7 plus 13 over x plus 2 quantity dx. You guys know how to do the integrals for all of these. What would the integral for that be? Plus c. And then you have the other stuff. Any questions on this problem? Okay. Are you guys good with this?
Yep.
Do you guys have any questions on the direct comparison test? Okay.
If you ever ask if we have any questions.
They're both. Okay, I'm just taking that. So both of them, you guys know the math behind everything. It's just knowing which to do when. So yeah, they will tell you to do the limit comparison test. And in actuality, I've never been tested on the direct comparison test. Having said that, you guys should still know because it could do a problem. Trig function with a direct comparison? I don't have one with trig, but let me check.
Oh yeah, it's the integral from I to infinity. Then it's 2 plus cosine x all over x.
2 plus.
Yeah, 2 plus all over x, then dx.
So did they use 2 over x for g of x? What did they use for g of x?
1 over x.
Okay. Yeah, the 2 shouldn't make a difference. So this is our f of x. Okay? The trick with direct comparison test is knowing what to make your g of x value. Okay? And it should be something similar to this. If we are going to infinity, the top numerator doesn't really matter because cosine of x oscillates and the 2 is just a number. Okay? So we can make our g of x equal to 1 over x. Okay? Now we need to know which one is bigger.
And so how can we just decide where does
The cosine of x goes up and down, right?
yeah.
So it's not going to affect the overall function once we reach infinity. Neither is 2. The only thing that's going to matter is the x. So we make our g of x 1 over x. Okay? Yeah.
Like it goes between, sometimes it's between -1 and 1. So the small it'll be 2, right? The small will be 1, right? So like, and the whole.
Yeah.
It'll be like, what, it was like 3 plus, and then they would have 2, you know what I'm saying? They wouldn't always have 1, they have.
Yeah.
It doesn't matter.
Okay. So now which one is bigger, f of x or g of x? They said f of x was bigger, right?
Yeah.
That should be true.
Yeah.
What was that question? Where g of x has been smaller or f of x? Okay, I did an example with e, 1 over e to the x squared. Okay, the g of x value that I used was 1 over e to the x. Okay, so once I used this and I did the integral of it, I found that this converges. So if the bigger converges, the smaller has to converge. So that's an example with g of x being bigger. So then what is the next step? The direct comparison test. So which is, we do the integral. Yeah, integral of dx from pi to infinity. Which is going to be what? What's the integral of 1 over x? So yeah, it is the natural log. Okay. So then we see that. So when you do the math behind it, you do need to show the limit as b approaches. Actually, you'd show that right here. And does this go to infinity? Yeah, because the natural log of infinity will be infinity. And since it goes to infinity, we know g of x diverges. Okay? Since we know the smaller function diverges, the function bigger has to diverge as well. Does that make sense? So let me do the 1 over e to the x squared quickly. Did I have limits on it? Do you guys remember what limits I had? Was it 0 to infinity? The one with the e? Like I did this one before. Or even the Friday session. But this was our f of x. So the g of x value that I chose was 1 over e to the x. Okay? 1 to infinity. Now, I found that the integral from 1 to infinity of 1 over e of x was equal to, was it a 0? Yeah. Was equal to a 0. So then this meant that g of x converges. So then the smaller function, the integral of 1 over e to the x squared d of x converges by direct comparison test. Now, if I had found that g of x diverged, what do I know about the original function? Nothing. So then what you technically could do is choose a new g of x value and try that. But the limit comparison test is a better test, because then you already know by doing the limit whether they grow at the same rate. You don't need to worry about whether it's bigger or smaller and stuff. Okay? So if you chose the right g of x value and you know that the two functions grow at the same rate, then you can be more sure. So on that note, let's do an example of a limit comparison test. Are you guys good with this?
You said equal to 0.
Yeah, g of x goes to 0, so we know it converges. Or it went to some value. It might be 1. I don't remember.
Or actually, whatever e.
Uh-huh.
Negative?
So it went to some number.
Okay.
And what does that number mean? It doesn't mean anything. Okay. It needs to be a number. It doesn't mean it grows twice as fast or 3 times as fast. No. Okay.
It doesn't have to be between 1 and 3,
No.
What is that?
I just made those limits up when I did the problem.
Comment, do they say like, it's greater than 1, it's less than 2? That number.
That's just when you do the limit of fx over g of x.
Raise grows.
Yeah. Okay. So what number you get actually out of the integral doesn't mean anything.
It means
Don't think it means it's like twice as much or anything. It just means that it diverges or converges. Okay, so for the limit comparison test, to prove whether it diverges or converges, let's do an integral from 1 to infinity of 2x plus 5 divided by the square root of x cubed plus 90 d of x. Something like that. So the first thing we have to find is what to compare it with. If it's 2x plus 5 divided by the square root of x cubed plus 90, the 5 and the 90 don't do anything as x approaches infinity. So the only things that matter are 2x divided by x to the 3/2. This can be made as 2 over x to the 1/2 as x approaches infinity.
That would be
That would be now our g of x.
X approaches
We still keep it, but yeah, we'll just go on with it since it was still a coefficient here. Actually, it shouldn't, but the problem that I'm looking at, the version of it, they do keep it.
Is that all we have to write, like, to explain that?
Yeah. So then, actually, they don't even share. Yeah. So, okay, so we'll just do 1 to infinity. So yeah, since the 2 in reality does not matter that much, so we'll just do 1 over x to the 1/2.
What would they care if we used to?
They shouldn't. They shouldn't. In the problem, they do drop the number that they have, but it shouldn't make a difference because you will see. So we have to do limit as b approaches infinity from 1 to b of x to minus 1/2 b of x.
And I'll have to check this where it goes.
Yeah, we know that if we had a 0, it would go, but we're going from 1 to infinity.
So do we have to show that?
We should do the X approaches infinity,
Yeah, like they made it so you have to like show it.
With the limit comparison test,
Yeah, they said it's like 3 steps, first step, how to do that, second step, show that the limit is in between 0 and infinity, third step.
that the
I mean,
limit,
they didn't do it in that sense.
they didn't. Normally, they always check for it when you're solving that improper fraction, whether you have to show it's improper or something, then you definitely do need to state it. But I don't remember ever them saying that you need to state it in like a limit comparison test, where you can just go and directly make b leading to infinity. If you want to state it, we can, since it did in class, but it's improper since upper limit is infinity as x approaches. I don't think it should be necessary though.
What they do want you to do is show that they grow at the same rate, though. The limit of infinity of
That is part of the progress. The first step, or did they call it a first or a second step?
I would probably a second step.
Okay.
I would say first and then you find you guys, and the second
Okay.
step you check.
We'll go with that. First thing, we need to know whether g of x diverges or converges. Then you can do the limit comparison test to see if they go at the same rate. We're doing the limit comparison test.
Yeah, that is a part of the.
Oh, they did it in a different order? Okay, it doesn't matter what order you do it.
Well, it kind of does. You check you guys, you find you guys, you check that it does grow at the same rate. If it doesn't, that means you take the wrong function and mess it up.
Technically, yes.
So then you definitely do that first.
On this, they don't do that, but that, makes more sense.
You check by doing the limit.
So let me do that.
You get a number, you get a good draw.
So, okay. So the next step, which they did beforehand in class, which makes more sense, is limit as x approaches infinity of f of x over g of x, and our f of x is 2x plus 5 divided by the square root of x cubed plus 90, all over 1 divided by x to the 1/2. You do that to see whether they grow at the same rate, and the answer should be 2, if I'm trying to do it correctly. The answer should be 2. If you do, solve it out. Any questions on this?
Why do you have to do that?
This stuff,
Why can't you just go on and evaluate it?
remember those like problems where we were trying to see whether it grows at the same rate, slower, or faster? We do this to know that g of x grows at the same rate, okay? So then, once we know it grows at the same rate, we can find the integral of how fast g of x grows, whether it diverges or converges. And since we know that they grow at the same rate, and we find that g of x they converges, we know f of x converges. Okay? Did that all make sense? It's just knowing the little parts of each test. It's not like hard per se. And then if you were to do this integral, you would get that it diverges.
What would happen if you just went ahead and solved it and found out it diverged? You have to do the step.
You still need to do this step to know whether it grow at the same or whether they grow at different rates. So let me summarize the two tests. Can I erase this? on Friday, you guys will learn, or Friday or Monday, you'll learn even more tests that you can do for different kinds of problems. Okay? So these aren't it. So the direct comparison test, the first step is finding g of x. The second step is comparing, so 0 is less than f of x, which is less than g of x, or a version of that. The third step is doing the integral of g of x. Okay? So then if g of x is bigger and we know it converges, then we know f of x converges. Okay? If f of x is bigger, or versions of that, which you guys should be good with now. The limit comparison test. The first step is finding g of x. The second step, I would say, is doing the limit as x approaches infinity of f of x over g of x, and whether that equals a number. If it equals a number, we know it's the same rate. And the third step would be the integral of g of x, and if that diverges, therefore f of x diverges, and versions of that. Any questions on that? Okay. That is pretty much it. So just be careful on this exam on doing the integrals right and such, okay? Don't make tiny mistakes and lose points. Make sure you go through all of the homework problems concerning different versions to integrals by completing the square or dividing or separating, because those shouldn't be hard, because since they're doing just integrals, you just need to know the little trick to doing them. And big O and little o, just review the problem I tried to teach. Otherwise, don't worry too much about it. And if you have any other questions, you can ask.